So this is homework 3, and homework 3 is talking about two tanks and some pipes connecting them. More specifically, it's talking about how Q1, there's two tanks that has flows Q1 and Q12 between them and Q2 out. Q12 has the equation half times root difference of the heights, and exit of tank 2 to the environment is a quarter times the root H2. Next, it says that the initial height of tanks 1 and tank 2 are 2 and 1.5 meters respectively. So this is good for knowing initial values of the differential equation when we integrate it. And finally, we need to ask to derive a governing differential equation for the fluid heights in tank 1, tank 2. We're going to do that by hand on paper. And then we're going to solve the resulting IVP using Python and Google Collaboratories. We also need to note that the time ranges from 0 to 100 seconds, and Q1 starts at 1 meter cubed per second, but then increases to 1.5 meters cubed at 50 seconds. So we need to account for that as well.
Hi, so this is the working out portion of the homework 3, and after going over the problem statement, so we're going to draw this out physically on paper now so we see what we're doing. So first things first, we have two tanks, tank 1 and tank 2, and we have a pipe going between tank 1 and tank 2. We're going to call it tank Q12. Pipe flow going into tank 1, call that Q1, and a pipe flow going out of tank 2, Q2. It should probably be at the bottom of the tank, but pictorially it does not matter. We know what Q1 and we know what Q12 and Q2 are equal to in terms of equation. So Q12 is equal to a half times the difference of the two tank heights squared. I guess now I should mention the tank heights are tank 1, height 2. Cool. And then Q2 is equal to a quarter times the root of the tank, height 2. Final bit of information about the tanks is they have a cross-sectional area A1 of 1 meter squared, and A2 has a cross-sectional area of 1.5 meters squared. What we want to find is dH on dt. And how we do that is we note that volume is equal to area times the height. Want to focus in, maybe? There we go. Sorry, but that was out of focus. V, so just to recap, A equals 1 meter per second squared. 1 meter squared, A2 is 1.5 meters squared. And we want to find dH/dt, and we're going to leverage the fact that V equals area times height. And how we do that is we know the flows going, or the change of volumes from each of the tanks, and we use that. So we have dV1 over dt, and we know that V is equal to A times H, so dA1 H1 over dt. And we know that this is equal to in minus out, so that's Q1 minus Q12. But since we know that A is constant, area is constant, we can pull that out of the differential and divide it over. So we now have that dH1 dt is equal to Q1 minus Q12 over A1. Similarly, we can do the exact same process to tank 2, where we have dV2 over dt equaling dA2 H2 over dt. But this time in is Q12 minus Q out, or Q out, which is Q2. And we can do dh2 over dd is equal to d12 minus q2 over a2. So this is the overall general equation. Just to recap, we have these two tanks. They have areas and heights specified. Flows going between those. Flows equations are here. And what we want to do is we want to leverage the fact that V equals AH, use that here, and then solve for the
So we're back here in Google Colabs,
So we're going
and
to go on to
now that
the
we have
coding
worked
part
out
of
everything
this
that we need to on
software,
paper, we're ready to start
actually.
coding. So first thing we need to import is numpy. We actually don't need to do this because I'm not planning on using anything that requires numpy, but it feels wrong to not import numpy, so might as well import numpy. Great. And so what we're doing here is we're integrating the actual solve IVP function command that we're using in Python. We're also needing to import from SciPy interpolate interpolate. We need to import enter 1D, that one. And finally, we need to enter from plotly. We need to do some plotly stuff. Some plotly dot subplot. I cannot spell. Oh, subplots. Import make subplots. Cool. Now, as for any coding problem, we need to define some variables to work with so we can reference things accordingly. So start with the tanks. They have tank 1 has a cross-sectional area of 1. Tank 2 has a cross-sectional area of 1.5 meters cubed. So the coefficients out front of the differential equation, we can call those whatever we want to. In case they might change in the future, we're going to make those variables. We're going to call first one alpha 1, 2, and that's equal to 0.5. And we're going to call the second one alpha 2, and that's equal to 0.25. Now we're going to talk about some constraints of the problem, like how we're talking about our initial heights, and we're going to have this be a array with noting that the initial heights are 2 and 1.5. And we're going to then talk about how long the code is running for, and that's for 100 seconds. So we're going to mark that as t end, and that's equally 100 seconds. Using that, we then need to talk about the flow rates here, how it starts at 1 and increases to 1.5. So in the code, that looks like talking about specifying flow rates at the flow rate of Q1 at those times. So we're going to call that the inflow rate. And we're going to get the values of that to be, we're going to call that Q1 actually. We're going to call those to be, sorry, Q1V for values. And we're going to call this 1.5 and 1.5. And this is because the 1 is at the starting, 1.5 is when it changes to 1.5 and ends also at 1.5. So we can change that to Q2 time or Q1 time, and that's equaling to when t is equal to 0, 50, and then 100. So now that we have, or well, It is 100, but it's good to call it t end here so we can change it in the future. So now that we have all our values mapped out, it's time to actually start writing in our actual code. So now we want to define a function dHdt, and it's going to have inputs t and y. I'll talk about y in a second. So we're going to have h1 equaling y of 0 and h2 equaling y of 1. This is just a way to quickly index these later in the future, so we can with relative ease reference them later in other functions. So now that we have this, we're ready to actually talk about the differential equations we solve. So for example, the dHdt of dH1 dt and dH2 dt. So for that, we're going to call this Q1 and Q2. So for Q1, 2, and that's equaling alpha 1, 2 times, I'm going to call this H1 minus H2. And instead of using NP square root, we're going to raise it to the 1.5 power. And we're going to have Q2 alpha 2. And remember that is equal to alpha 2 times root 2 to the 1.5 power as well. Now it's time to actually do the differential equations. So dH1 dt, and that's equal to our if you remember, that's equal to our flow in, our Q1, minus our flow out, Q12. So that looks like Qn at some time t. We don't really need to define t yet, and then minus Q12. We divide that by a. Now we have dH2 dt, and that's equal to the same thing but a slightly different, Q12 minus Q2, and divide that by the cross-sectional area A2. Ooh, this should be A1. Sorry about that. A1. This needs to be the function still. Cool. And then we can return dH1 dt and dH2 dt. Okay, so sorry I had to cut there. I made a mistake and couldn't find it, and then when I looked back and found it, I just missed a lot of dumb stuff. So for clarity's sake and conciseness, we're going to pick up back here. So last thing we did is we returned the actual values out of dH1 dt and dH2 dt. And this is where we actually start to use our functions, and we're going to call this, we're going to now gather all this data and bring it into one thing that the next functions to solve IPP can make and turn into, and then solve. So what we want is we want to take Q1V as our first one, as our xy, and Q1T as our Q1T as our first, and Q1V as our second. And then we want to have a kind equaling previous. And then we want to have the result now take what we interpolated here and then use the actual IVP. So solve IVP dH dt, and we want it to go from, we want this band to go from 0 to t end, and then we want y naught to be our initial hi. We want our method to equal Radau, and we want our dense output, so we can see, we want our dense output to be true, so we can then more easily work with all of their data that this outputs. Finally, we need to actually define what t is explicitly, and t is our np.lin space. So I guess I did lie to you earlier when I said I wasn't going to use numpy, but what can you do? I'm gonna call this barely counting as using numpy because I'm using it once. Anyway, RT is gonna range from 0 to t end with 100 values, not 1,000. Oh boy. In the middle, and then we're going to call this, and then we're going to have our solution equal the results dot sol of t. So that's how we got it. So if I want to like type out sol, this brings up our solution where it starts at 2 and starts at 1.5, and then it gets gradually bigger and bigger up until we get to 1.18. And that's because, and it's going up because our input is going at 1 here, and it's not exiting quite fast enough because our Q2 is so small. Anyway, so we can now move on to the graphing portion of this. So that's just making a plot. We already have all the data, so now we're just taking a plot. So make subplot. We're gonna have rows equaling 1, columns also equaling 1. Yeah, well, that does work, don't. Sorry, and then we're gonna have fig.add scatter, where we're gonna have our x equaling t, and we're going to have our y equaling solution value of 0. And we're going to name this, name equals h1. h1. And if we do this, ooh, wow, we have a scatter. Man, look at me go. And then next we're going to add the next line on top of that. So that's scatter, add scatter, x equaling t, y equaling this value of 1. The second element, it's the first, but it's also the second because Python, remember, indexed at 0, name equaling h2. And we got this here now. Now it labels because there's 2 lines, but as you can see, t is going from 0 to 100, and it looks like this. Here at 50, we see the bump of h1 going up higher, faster, because it feels it more immediately feels the change in height based off, or more immediately feels the change in flow rate, and h follows along quickly after, getting a slightly higher increase. We can add a quick fig dot We can add some titles if you want to. So update layout. Update layout. And that would be dict x-axis. And we're going to call this I don't know, time in seconds. And then we're going to time in seconds. And then we're going to have a y-axis title equaling height in meters. And this should be the end. So we have a time and a height, and that's really all you need for a graph. So that's homework 3 done. Thank you.